Hello everyone. This is a lecture about stability and transition of boundary layer flows. So transition is basically the consequence of stability instability arising in the flow. So transition from laminar, which is a smooth flow, to turbulent flow, which is a chaotic flow, is a very complex phenomena. And one of the reasons to study this complex phenomena transition is that, as you can see the figure over here, where as the flow moves from laminar to turbulent, as it transitions, the skin friction drag increases very significantly, and there is increase in surface heat transfer, and that changes the vehicle performance. And uh, if we can predict the transition accurately, we can design a very efficient vehicle. So the role of stability analysis in transition is that, let's say I have some sharp geometry flowing at high speed and some shock wave ahead of it, and then there is a free stream disturbances that comes into the flow, and these disturbances move in the boundary layer, and depending on the condition of the flow, these disturbances which is coming from the free stream can grow or decay. So it becomes very crucial to understand how these disturbances behaving in the flow, because that is going to decide that when and where the flow is going to transition. So this is a typical schematic over here that shows that what are the different mechanisms happen in the flow before the flow suffer transition. So here it is showing an enlarged view of what's going in the boundary layer. So we have a flat plate over here, and we have this dashed line which is a boundary layer edge line. And receptivity is a process by which any disturbance which is comes in the flow enters the boundary layer, and through this receptivity process, the any of the disturbances, when I say disturbances, it means like it is a fluctuation in terms of pressure, velocity, or temperature. When these disturbances enter into the boundary layer, it become a wave, and that wave, depending on the flow condition, can grow or decay. So in the initial stages, this instability wave, where whether it can grow or decay, that region is basically known as primary instability. Once it passes from the primary instability, then there is a secondary instability, where the multiple grown wave have tendency to interact among themselves in the secondary instability. And then there is a nonlinear breakdown, where multiple waves start to interact and the process become completely nonlinear. And then it goes to turbulence. Now, depending on the amplitude of the flow, the depending on the amplitude of the free stream disturbance, the flow can have the primary instability, or it can escape the primary instability, or it can even escape the secondary instability, and it can directly go to the nonlinear breakdown. So in those scenarios, when we have the high amplitude disturbances, it it bypasses this all instability mechanism, and it directly goes to nonlinear breakdown, and then flow suffer turbulence immediately. You will also notice that the primary instability region is much longer compared to the secondary and nonlinear breakdown, because once the secondary instability starts, it is very small time to go to the flow to the turbulence. So it become very crucial to know that what's going in the primary instability, because primary instability is the one which decide that what is going to be the amplitude for the secondary instability, and that decide the nonlinear breakdown and the turbulence. Yeah, so we discussed this figure. Now here in the right hand side we have a flow chart that is basically showing that what are the different paths the flow can take depending on the amplitude of free stream disturbances. So if we have the low free stream disturbances, which is a realistic scenario when you have the body flying in the air at certain altitude, there is going to be realistic scenario low amplitude perturbation, that is a small fluctuation in pressure or velocity or temperature. In those scenario, it follows the primary instability, secondary mechanism, and then breakdown and then turbulence that we are seeing over here in this figure. But when we have high amplitude disturbances, such as if the body is flying externally at certain altitude and some external objects enter into the flow, in those scenarios we can see that from the receptivity process it skips all these instability mechanism, which is a primary and secondary, and it directly goes to it directly bypasses those mechanisms, and then it goes to breakdown and then turbulence. So as we see in that, the primary instability is longer, which is which we call as a natural transition, because that is happening because of the realistic scenario. And this primary instability region is a linear phase that decide what is going to be the amplitude for the secondary and maybe tertiary instability and then nonlinear breakdown. The nonlinear phase is the secondary, and the nonlinear breakdown regions that leads to turbulence, it occurs very quickly. So it is very difficult to even study the secondary and nonlinear breakdown. It is complex because there are many loose ends you will have to figure out, such as if the waves are interacting, what is going to be the phase angle and their amplitude. So it becomes crucial to understand the primary instability, which is much longer and play a significant role in deciding the final amplitude for the wave. So primary instability is a linear stability, and it decides what will be the amplitude of disturbance at the beginning of the secondary mechanism. Now, talking about linear stability, we have two different ways of doing it. One is the numerical way, where we perform the DNS and we enforce very low amplitude disturbances in the flow, and we let it evolve with the flow, and then we save our flow field, and from the flow field we do different analysis to track those disturbances which we put in the flow. And then there is a theoretical approach which is popular in the literature as a linear stability theory. So it basically takes the laminar mean flow, and on that, in a mathematical way, it imposes the disturbances, and then it reduces the set of ordinary differential equation to a eigenvalue problem, and through the eigenvalue problem it tells us that whether the flow is going to be unstable or stable by studying the different frequency in the flow.